Okay, we're going to start into P.3 here, where we're talking about radicals, which when you think of a radical, think of a square root or a cube root or so on, and rational exponents. Rational meaning that they're written as fractions. And so those are the two types of things that we're going to look at. We're going to be looking at radicals, those square roots, a type of problems, and also the rational exponents, which are exponents that are fractions. Okay, so first there's a couple of properties for radicals that we need to talk about. Any radical, and this could be a cube root throughout, or it could be a fourth root, whatever the case may be. If there's multiple things inside of a square root, we can separate them as long as inside they were multiplied, then we can do multiplication on the outside. Think of it like the square root of 9x. Well, I don't know the square root of 9x, but if I separate it as the square root of 9 times the square root of x, I do know the square root of 9 is 3. I still don't know the square root of x, so I can leave that there, but now the problem's a little bit easier to look at, or easier to work with. And so these kinds of simplifications we can do. Multiplication inside means multiplication between the roots. Consequently, we have a very similar result that when we have division inside of a root, we can split it into the division of the two roots. So something like the square root of 3/25. Well, I don't know the square root of 3/25, but if I treat it as the square root of 3 over the square root of 25, I still don't know the square root of 3, but the square root of 25 is 5. That at least simplifies the problem somewhat for me. Okay, so multiplication inside can be separated, and division as well. Okay, so those are two big properties we're going to use for simplifying. Now, if we wanted to add or subtract radicals, a couple things have to be the same. The inside of the radical has to match. It's a lot like terms. So here you see that if we had 2x plus 5x, well, you'd get 7x. The x doesn't change. You just add the numbers in front. Exact same thing here. We're going to pretend that root 2 is the x in the problem. 2 root 2 plus 5 root 2. We're just going to add the 2 on the outside and the 5 on the outside to get 7, and of course we just keep the root 2 the same way we would have with the x. Same process works for subtraction. 14x minus 4x is of course 10x. So 14 root 3 minus 4 root 3 would equal 10 root 3. These two rules, that we can, it's the same, we just focus on these outside numbers. It's a really important rule for simplifying roots. As we condense equations and expressions, we need to be comfortable with this process. But of course, these must match. If not, if this was 14 root 3 minus 4 root 2, that would be like 14x minus 4y. And you cannot combine x's and y's. So you wouldn't be able to combine that. So that is a different situation entirely. The roots must match. Now sometimes in the book, you're going to come across problems where the roots don't match. For instance, the square root of 48, square root of 3, and square root of 75 might initially seem like they have nothing in common. But if we try to break them down, okay, 48 divides by 3, which I'm hoping to have, and 16. Now those are both still inside the square root. That's why you see the square root of 16 times 3. But what is the square root of 16? The square root of 16 is 4. So that gets to come out of the square root. Did I know the square root of 3? The answer was no, so it stayed inside. But what's nice about this is now I have root 3 and root 3, so I could combine those. 75, if we divide it by 3, again, we're trying to hopefully find a 3 for all of them to match. Turns out that 25 goes in 3 times. Well, the square root of the 25, we know that to be 5. And so now I have 4 root 3 minus 1 root 3 plus 5 root 3. 4 minus 1 is 3. 3 plus 5 is 8. Hence 8 root 3. Now that's one that was kind of given to us as an example. Let's see if we could break this one down. Now you could choose either of these two guys to work with to start. But what's really important is that we just find one that we think is easy to work with. I actually really like the 50 over here because I know 25 goes into it. So I'm going to write square root of 25 times 2. Okay? because 25 times 2 is 50. Of course, we have our 3 out here. Now, I'm going to be really cautious the way I do this. I'm going to write 3 times square root of 25 times the square root of 2. You remember in that first slide we said that we could split this into 2 different square roots. Now, I could come back here and work with this, but I'm going to wait for a minute. This 25, what is the square root of 25? Well, we know that that is a 5. But notice, it's 3 times 5, which is 15 times root 2, so 15 root 2 plus. Now I need to come back here and do the same process here on the right. One important idea, though, and I hate to say, that math is always perfect, because it's not, but in problems like this, we want to try to make them perfect. And because there was a leftover 2, I'm hoping that with the 32, I would have a leftover 2. And so I might divide in my calculator. 32 divided by 2 turns out to be 16. And of course, we have our 2 out there. Now this is really nice because 16 does have a square root. If it didn't divide evenly, I would just go back and start from scratch and try to break the 32 down by myself. But I'm hoping to be able to compress these. And in order for that to happen, I need that root 2 to be left over. So here I have 2 times the square root of 16 times the square root of 2. Now 2 times 16, that is 32, so I haven't changed anything. But 16, when you take its square root, is really a 4. And 2 times 4 is 8, with a root 2 left behind. Now 15 root 2 plus 8 root 2, I add the 15 and 8 to get 23 with a root 2 left over. Notice the square root 2 did not change, because when you add things, it's like adding x's, they get to stay the same. Okay. Next we have what's called rationalizing the denominator. There's a, if you will, a policy throughout mathematics that we don't like to leave square roots in a denominator. And so we want to try square roots, cube roots, and such. We want to try to get those out of the denominator. The way we do that typically, if it's a square root, is by multiplying by the exact same thing that's in the bottom. So for instance, if I had 4 over root 3, in order to get the square root of 3 out of the bottom, I would times the top and bottom by the square root of 3. On top, you would end up with 4 root 3, which you could see sort of that a root b. But on bottom, the square root of 3 times the square root of 3 is the square root of 9, but the square root of 9 is itself 3. And so you can see how they sort of just took the b out of the square root. So we're like taking this 3, saying I'm going to multiply by its root, so I'll just bring it over here as a 3. Let's look at one more example down here, and then I have to talk to you about a special case. To get the root out of the bottom, we ask ourselves, what is in the bottom? Right now it's a root 2, so I'll multiply by root 2 on top and bottom. And this will produce 1 root 2, or simply root 2, over square root of 2 times square root of 2 is the square root of 4, right? But the square root of 4 is really 2. And there's our answer. Now there are, from time to time, problems where rationalizing the denominator is not that simple. Let me look at one of those with you. Let's say we had 3 over 2 plus the square root of 5. Something you have to understand right now at the face is that there's something besides just the root down here. This 2 plus the root 5 really makes things a little more complicated. If I multiplied by root 5 on the bottom, the square root of 5 times the square root of 5 would be 5. But that square root of 5 would also have to multiply by this 2, and it wouldn't get me anywhere. So we use what's called the conjugate. This is something that we'll use again and again throughout the year. The conjugate is the partner to the 2 plus root 5, but it needs to be slightly different, and I'll show you how. Instead of using 2 plus root 5, we're going to use 2 minus root 5 on top and bottom. Now, all you'd have to do is switch this sign here. If you had 3 minus root 2, you would multiply by 3 plus root 2. We're just taking its opposite, its partner. Okay? Here we do simple distribution. 3 times 2 is 6. 3 times negative root 5 is a negative 3 root 5 all over, and this is where it gets a little bit messier. We have to FOIL here. What's 2 times 2? It's 4. 2 times a negative root 5 is negative 2 root 5. There are no shortcuts the first few times through this. You really need to make sure you understand all of the steps. Root 5 times a positive 2 is plus 2 root 5. And then a root 5 times a negative root 5 is a negative root 25. Okay, now in the middle, you'll notice right here, these are identical partners. Okay, negative 2 root 5, positive 2 root 5. They should always cancel, leaving me with 6 minus 3 root 5 over 4 minus, and we have to ask, what is the square root of 25? It's 5. Notice right now there are no square roots in the denominator. That was our whole goal, was to get the root out of the bottom. This problem ends up a little weird towards the end. It's 6 minus 3 root 5 over 4 minus 5 is negative 1. Typically we don't leave a negative in the bottom like this, the sign, and also dividing by negative 1 won't change the numbers. It'll just change their signs. So 6 divided by negative 1 is negative 6. Negative 3 divided by negative 1 is a positive 3 root 5. So this turns out to be the answer. It's kind of weird. It doesn't have a denominator anymore. I made that up as we went, so bear with me. There's a few oddities to it. But this right here is the crucial idea, that we know what to multiply with, and then we distribute properly. Okay? So that will happen in the homework. It's likely to happen on tests. We need to be comfortable with that process. Now, sometimes we get roots that aren't square roots. In this case, it might be a cube root or a fourth root, anything like that. What we have to remember is the basic rules are the same. The big difference is that to get out of a cube root, because we can't keep track of every cube root, we need 3 identical things. So if I break the 24 down, I'm going to get a 2 and a 12. The 12 breaks down as a 2 and a 6. And the 6 breaks down as a 2 and a 3. So I've used the 6, I've used the 12, I've used the 24. Well, what do I really have in here? Turns out this is really the cube root of 2 times 2 times 2 times 3. If I really want to look at what's in the 24, this is it. And notice there are 3 2's. A cube root needs 3 identical pieces, so this comes out of the cube root and is a 2. Then I rewrite the cube root symbol, and anything that was not part of that group gets left behind. In this case, the 3. Okay. If there was a 5 over here, 3 times 5 would be 15, and I'd leave a 15 there. Whatever's left over gets left inside the root. It was a cube root before, it's still a cube root now. All I did was find 3 identical pieces to pull out. Here, we want to do the same process, but it's a multiplication problem. Well, the same rules apply for multiplication that we had before. I can multiply 8 times 4 to get 32. But I'd also like to see if it breaks down the way that the cube root up above did. And so I started thinking about 32. I know it's 2 and 16. The 16 would be 2 and 8. The 8 would be 2 and 4. And the 4 would be 2 and 2. So these other numbers have all been used. And so this is really the same thing as the fourth root of 2 times 2 times 2 times 2 times 2. 5 of them. But because it is a fourth root, I need to find 4 partners. I see them right here. they can come out of the square root and represent a regular 2. Or out of the fourth root and represent a regular 2. Then in the fourth root belongs anything that didn't come out. That would be this guy right there. I had one too many 2's, so it got left behind in the pile. Well, that's multiplication. Division, very similar. I can split this. So 125 doesn't divide by 27. So I'm going to split this as the cube root of 125 divided by the cube root of 27. Now I know I'm not supposed to have this root down here, so my first focus is on this denominator. Well, a 27 is made up of a 3 and a 9, and a 9 is made up of a 3 and a 3. Well, it takes 3 threes, or it takes 3 of something to get out of this. So this is the cube root of 3 times 3 times 3. Well, that's all of the numbers inside the root is what it takes to get out. So this turns out to just be 3 on bottom. On top, I want to start looking at this. I think a 5 will go in there, and it goes in 25 times, which makes it 5 and 5 again. Well, how many 5s do I have? This is the cube root of 5 times 5 times 5. And sure enough, that's all 3 of them. To get out of the cube root, I end with 5 over 3. And that's the answer. So we can split them and work on them individually. We can multiply them together and work on them together. All right, so we come to the last slide here. Talk about rational exponents. Rational exponents are just exponents that are written in fraction form. Okay, and that they can also be written as fractions, but they can also be written in this radical form. Okay, notice the bottom here goes right out here. Okay, and then the n, the higher exponent, the top one goes here. Okay, so we just want to be able to go back and forth, and let's look at these two examples. Okay, if I were to write this in radical form, first thing I might do is put the radical there. Now I know a 4 goes inside of this radical. That's this piece. Done. Question is, what goes out here and then what goes inside there on the 4? Well, if we look at the structure here, the bottom value always goes here and the top value always goes and stays on top of the number. So it's the square root of 4 cubed. Now I could obviously simplify this sum, but I'm going to leave it. I just want to see if I can make the transition between one and the other. Now normally a square root doesn't have a 2 written here. Usually you see nothing. And so if you see nothing, just assume that it's a 2. And then over here we have this 16 to the negative 3/4. One of the first things I want to do, we talked about before last time, was these negative exponents. Negative exponents mean we need to flip this. Since this is 16 over 1, I'm going to make this 1 over 16 to the positive 3/4. Okay? And so what I'm going to do now, I'm going to do 1 over, here's my root, here's my 16. This part of the root right here is the bottom of the fraction, which would make it a 4th root. And it's 16 cubed. Now, coincidentally, okay, 16 does have a 4th root. And if I were to try to simplify this further, I'm going to go ahead and stop here. Or I would have even accepted, if you'd gone this way, the 4th root of 16 to the negative 3rd. I would have allowed this as well. There's a lot of different rules that are going on in college algebra, and we're trying to keep track of each of them. And so if we look at this 1 over 4th root of 16 cubed, I could also write it as 1 over the 4th root of 16 cubed. I could put the cube on the outside. It's interchangeable. Well, the 4th root of 16, if I checked in my calculator, turns out to be 2. 2 to the 3rd power is 8. This really reduces to 1 over 8. We'll see how much we go through in class and how we might tweak some of those and talk about some of the problems, and we'll see you in class. Good luck.